Hello, everybody. Good morning, good afternoon, good evening. I don't know where you guys at, but thank you for being here today. I'm Laura. Nice to meet you. And I have with me Evan over here. We'll present a bit more of ourselves later. But yeah, I heard we need to chit chat a little bit for a couple of minutes to give you time to log in and feel ready for it. So before we start, I don't know if you guys have seen this platform yet, but any questions that you guys have, go ahead and do it on the right side. We're going to see them and we're going to answer them at the end. So just keep them coming. It doesn't have to be at the end. You can, whenever you have that question when we're talking about it, just mention it and we'll answer it at the end. Okay. So yeah, hope you like it. And I think that's all I need to comment for you guys. If we don't get to cover your question, do not worry because we see it and we will answer it on email separately. I hope that's the case, that you guys ask a lot and we need to respond on email. That would be great. But yeah, apart from that, we will be sending the recording, so no worries about that. You don't need to record or do any screenshots of anything that you're going to see. We will send that afterwards, as well as any other things you might request that you want to see. We'll also include that in the email, okay? So having said that, I think I did a good job at chit-chatting and we can go ahead and start. Again, thank you everybody for being here today. Today we're going to be talking about mitigating extreme weather risks with advanced data in solar designs. So we go ahead for the next slide. Let me go ahead and present myself first, since I'm first, although it's a bit rude, but I'll go ahead and say I'm Laura. I'm based in Barcelona. I work for RatedPower, which is headquartered in Madrid. And I'm business developer in international trade in the APAC region and North American and European markets. With me, I have Evan, product manager at Clean Power Research, enhancing solar resource and weather data for PV projects, working with us for a while now with their solar resources on RatedPower. Thank you for being here, Evan.
Yeah, thank you.
Perfect. Well, let's keep going and talk about our agenda today. First of all, we're going to do a brief introduction to RatedPower. Then Evan will take the lead and talk about SolarAnywhere, deriving SolarAnywhere, the importance of high resolution data, accounting for extremes, wind and smoke. Then I will take the lead back in and showcase RatedPower software and how do we have SolarAnywhere data on the software. And later we'll have a Q&A session. Okay. That being said, let's go ahead. Let me talk a bit about RatedPower. On the next slide, we even have some pictures of it. If you've never seen it, this is how it looks like. This is the tool that more than 2,000 users use worldwide daily. I like to say always from Canada to New Zealand, from Chile to China. We have users all around using this tool to design their solar plants. And not only solar plants, we would also include design and engineering of battery storage, of substation engineering, and of your overhead line. What do we say when we say design and engineer? Basically, what you're going to be able to do is logging on this software, which is on the cloud, select different equipment parameters, compare, really quickly compare how one equipment would iterate and change your results from another. Change different metro resources, such as the ones we have here, or just change specific technical pitch distances or things like that on your solar designs. Every time you do a change, we would have an algorithm behind it running the simulations and giving you an automated yield. But not only a yield, it would also include information such as your bill of quantities, your layout in AutoCAD format, your SLD, reports, all of that for all of the engineering things that I mentioned before. So not only the PV part, but also substation, overhead line, and battery storage. Just last week, we launched a standalone battery storage, by the way, so really excited about that one. But yeah, why are we here today? Well, RatedPower started, what was it, 8 or 9 years ago already. It's been a while for sure. Back in the day, we were a small startup. Now we are 150 plus in Spain, but as part of Embers, we are a lot of people worldwide. It started as calculating that yield at the beginning, right? The founders of RatedPower used to do this work, and it took ages to do it. How did they do it? Well, metro resources are key. And that's why we're here today, because metro resources, having the right resources, are going to be key to giving you the best yield, which is going to help get your project bankable and go to the next stages of construction. So I think that's a brief, hopefully as brief as I could, introduction of RatedPower. And with that, Evan, if you want to take the lead, go ahead.
Yeah, that is fantastic. Thank you, Laura. Hello, everyone. My name is Evan. So I'm a product manager here at Clean Power Research for the SolarAnywhere product line. And within SolarAnywhere, I specifically manage our historical data products and services. So a little bit about what we do at a high level. We provide global solar resource data and intelligence services to support solar project development and operations. And we do this with a number of different products and services for all stages of a PV project lifecycle. So for example, the SolarAnywhere product line offers historical data for prospecting and design, real-time data for operations, and forecast data for energy markets, DERMS applications, and hybrid operations. I'll note real quick though, it's important to understand that the data generated for each of these time periods comes from a different data model. So for example, the historical model relies on data generated from satellite images, whereas things like the real-time model rely on numerical weather prediction models and some real-time satellite images to do things like cloud motion vectoring. So today I want to highlight that I'm specifically going to focus on historical resource data and how the SolarAnywhere historical model produces data that can enable folks to minimize project risks and more accurately anticipate project performance. I'll also note that within this presentation, I'll address the benefits of high-resolution data sets, how high-resolution data can be distilled into typical year file formats for design and prospecting, and the importance of wind data in the design process, and smoke impact from wildfires and how our data model can account for it. So before jumping into the details of our data, I wanted to spend a few minutes talking about how we're even able to generate solar resource data at such high precision and at a global scale. It's really quite amazing, and it's really easy to look past the complexity and scale of generating this data. So first, the SolarAnywhere data model uses different clusters of satellites, which are positioned around the globe to generate data in real time. And so what I'm showing here is the GOES-18 satellite, which is owned and operated by NASA, and it is positioned over the Western Hemisphere. And this satellite is one of the many sources of imagery that we rely on globally to produce our data sets. I think we have 7 or 8 other geospatial satellites that we rely on positioned globally. And a few interesting details about these satellites. So this is a geospatial satellite, as I mentioned, which lives at a fixed position above the Earth's surface, rotating at the same rate to maintain this constant position in the atmosphere. And these are the primary types of satellites we rely on. However, we also use polar orbiting satellites to capture imagery at higher latitudes. And so these polar orbiting satellites do not stay at a fixed positions, but they orbit over the poles, as you may have guessed, to capture images as they're moving. And both of these types of satellites capture a variety of bands of data. So this includes infrared data, ultraviolet data, and visual imagery. And once we have these images, the SolarAnywhere model then processes the raw satellite data with our patented method for irradiance modeling. And just a fun fact, the advanced baseline imager, which I highlighted on the screen just now, it's the camera that we get our data from, our images from, costs approximately $100 million. So these are not cheap pieces of equipment. They're very expensive, and we're very dependent on them. And so next, this is what those images from the satellite look like when they're stitched together over time. And you can see the complexity of the cloud motion in each image with distinct cloud types, dispersion, and velocity in different layers of the atmosphere. And as satellite technology improves, so new satellites come online all the time and are launched into orbit, we incorporate them into our model to maximize the spatial resolution, or the pixels in the images, and the temporal resolution, which is the image frequency within our data. And doing this at scale is definitely not easy. We process more than 100 million images, or 1 million images rather, and billions of pixels every year to calculate our new historical data models with each new data version release. So data resolutions, as alluded to on the previous slide, are often thought about in terms of temporal resolution and spatial resolution. And temporal resolution is the frequency at which the images are taken by the satellite and incorporated into our historical model. So in this graph, we can see a comparison of the estimated irradiance from different resolutions at the same location over the period of a day. And a few impacts that you'll notice in this graph of the lower resolution are, first, we can see some time shifting errors that are exacerbated in the hourly time period. So as you can see, that hourly resolution has the largest magnitude of these time shifting errors, whereas the 5-minute data much more closely represents reality, or what we'd expect at the solar panel. Resource variability is also something that can be improved with higher resolution data. So the irradiance values are very flat within the hour period, which you'll notice. You'll also notice that the hourly resolution has the lowest peak irradiance value, whereas the 5-minute intervals have the highest peak irradiance value. And I think looking at this graph, the difference in these peak irradiance values is approximately 80 watts per meter squared, which is quite significant. And although that total solar resource throughout the day, or that total insolation, should be similar, in some cases you can even see some underestimation of yield in those larger temporal or lower temporal resolutions because it's not able to capture some of that variability. So similar to the last slide, this shows a comparison of temporal resolution, but based on what the images look like when stitched together at 30 minutes versus 5 minutes. So you'll notice here that the image on the right is much smoother, and it almost looks more like a video. If you were to zoom in on the clouds on the right-hand image, you'd see something more similar to the 30-minute image in terms of the amount of space that it takes up, but you'd see that the cloud cover per pixel is changing much quicker than the left-hand image, which is really what equates to more variance, similar to what was shown in the previous graph for high-resolution data. So next, I want to talk a little bit about spatial resolution, which is another important component of high-resolution data. So spatial resolution is really understanding the variance and improving the precision based on the image quality. So this is determined by the number of pixels in the image used to derive the irradiance data. And you can see the resolution labels here of 10 kilometers, 1 kilometer, and 500 meters atop of each of these images. Those measurements represent the area on the ground that a single pixel within the image file covers. So looking at the images from left to right, you can see it gets easier to see these holes within the cloud cover, especially towards kind of like the right bottom hand part of the image, which on the ground would really result in more direct sunlight or more solar potential. So similar to having images more frequently, having images with more pixels can also increase that variability captured within the model. And this can have those same design implications on things like inverter sizing and string sizing that the higher temporal resolution can also have. And so next, this is another view of spatial resolution. So spatial resolution is especially important when considering systems in complex weather regions. So in the areas that are on the coast or in mountainous regions, as opposed to places like the desert. And what these images here are showing is a comparison of the average irradiance over a typical year. So one is at 10 kilometers and the other is at 1 kilometer. And in the image on the right, that blue represents the percent of negative change compared to the 10-kilometer tile. And the red represents the percent of positive change compared to that 10-kilometer tile. So in other words, both of these squares represent a 10-kilometer area on the ground, but the image on the right breaks that 10-kilometer area into 1 kilometer squares, which really provides 100 times the resolution. And at lower resolutions, irradiance values are subject to spatial averaging over what might be a dynamic climate region. And this averaging really does not reflect the true resource characteristics of where the asset might be built after site selection. At higher resolution, we see that solar potential really vary significantly, In fact, in this example on the right, moving just 10 kilometers north can result in nearly 2% higher resource over the lifetime of an asset, just because of these resource cliffs that can exist within a 10-kilometer area. A thorough resource assessment should, of course, account for climate variability at the site, but utilizing high-resolution satellite data can definitely be an optimal guide to site selection for long-term asset returns. So next, I'd like to briefly talk about typical year data sets. SolarAnywhere offers irradiance and weather data back to 1998 in most regions globally, and at these different resolutions of 1 hour, 30 minutes, and 15 minutes, and even at 5 minutes within the continental United States. However, most often, typical year data files are used in the solar design process, which traditionally includes hourly intervals. This is why you might often hear TMY files referred to as 8760 files, as there are approximately 8,760 hours in a year. However, some PV design platforms, including RatedPower, now allow for sub-hourly typical year files as an input to their platform. So we can take the high-resolution data that existed as long history timestamps and manipulate them into typical year file formats. And this is a really big deal, as sub-hourly or higher resolution typical year files enables the best of both worlds. There are smaller file sizes that represent a typical year over the past 25 years, but they also still enable us to capture accurate daily variability with those sub-hourly temporal resolutions. So this graphic shows just how a typical year file is created. Instead of taking average values over the full history to create a smaller file, we can incorporate each month over 25 years and take the month closest to the average. And this ensures that we capture that daily variability, which I mentioned, which having that high resolution data further helps with. So for example, a typical year file could consist of all the days within January from 2007, and then all the days from February, say in 2020, and then all the days from March, say in 2015, and so on. So high resolution is very important in capturing variability and increasing precision, and using high resolutions in typical year file formats make it even easier to apply precision to the solar design process. But now I want to transition the conversation into the topic of wind data and the impact that smoke can have on PV performance. So wind data is another important factor in terms of anticipating project risk and modeling asset performance. And in this example, we've generated a map of Western Europe on the left, and you can see in yellow the areas of the highest wind gust taken from a typical year file. So this is created from a SolarAnywhere typical year file. We've also compared the typical year distribution of maximum wind gust values at the two locations. So you can see this on the right, designated as Site 1 and Site 2. And you can see that there's really a drastic difference between the maximum wind gust at these locations. So Site 2 is very extreme, whereas Site 1, the distribution is more irregular, implying that you can expect much less intensive wind gusts on average. So why is it important to compare these wind gust values? Well, in windy regions, wind stowing strategies are often considered to reduce the risk of panel damage due to high gusts. And it's important to note that our data captures the highest wind gust predicted over a period of time. So while it might still be important to use ground measurement of wind to capture these fields at more frequent intervals or higher, even higher temporal irradiance or temporal resolution, the SolarAnywhere data will still provide the maximum wind gust that you should expect at a location, which can be very helpful to have early in the prospecting or design phase to understand that wind risk. Wind data is also important as an input to solar design to calculate performance impact. So, for example, cooling effects can occur from wind on solar panels as it reduces their operating temperature and has potential to increase their efficiency. And of course, that's depending on ambient temperature as well. Cooling factors can also increase the longevity and minimize the degradation of panels. And then I also want to mention dust and debris removal. Wind can help by reducing soiling by removing the dust and debris from the surface of the panels, which I'll talk a little bit more about on the next slide as well. So lastly, smoke impact is a topic that has become of increasing concern recently. We've seen a lot of wildfires leading to several smoke events occurring in the Western United States and Canada. And I know similarly, Spain has felt this, as have countries like Australia and Brazil. So this graphic is made up of images from the GOES-18 satellite, which is the same satellite that I showed earlier that we use as a source in our data model for the western part of North America. And it is overlaid on a map of the northwestern United States and western Canada. And smoke is really, really interesting from an aerial view. As you'll notice, it looks very similar to cloud cover, but really it's just particulate matter. And you can see this in this image, as the difference between smoke and the clouds is very obvious at first, but especially in this upper right hand or upper left hand corner rather, it becomes much less obvious as that cloud cover moves into those smoke areas. And so within our irradiance model, we're able to account for smoke in a few different ways. First, as you might expect, we can pick up on some of the impacts of smoke through the visual imagery, just like we do with clouds. But in addition, our model includes an input for something called aerosol optical depth, or AOD for short, which is accounted for when we identify how much irradiance should be occurring in clear sky conditions. So this ties into the model when we're identifying what irradiance should occur without any clouds. And so this aerosol optical depth value is generated by numerical weather prediction models. And really it's a quantification of aerosols such as dust and haze, ash, sea salt, etc., that are distributed between the surface of the Earth and the top of the atmosphere. And AOD is inclusive of particulate matter, of course, as well, which these values can be downloaded as unique data fields from the SolarAnywhere platform. And I will note that most of the particulates from smoke are captured within the particulate matter 2.5 field, as smoke primarily consists of very fine particles. So although it's not quite exact, there are ways to approximate smoke by pulling particulate matter data at 2.5. So next, let's look at these visuals, which represent smoke and the impact that smoke can have on asset performance. So first, the visual on the left-hand side is a representation of specifically smoke particles in the air from a wildfire. And these particles, in addition to other particles that are not attributed to smoke in the air, have an impact on how much sunlight reaches the surface of the Earth. And this smoke data shown here, I'll note, is something being pulled from an external data source provided by NOAA that indicates only smoke, so it excludes other types of particulate matter. Next, if you look on the right-hand side, this is a representation of the impact that smoke has on energy output of a PV system. And this was created using SolarAnywhere's model at the same location and at the same time that we see smoke occurring. So you'll see here a lot of those impacts, they start at the center of the image, but then as the smoke spreads, it also distributes within that right-hand graph to affect PV performance. And so something I'll allude to next is that it's very noticeable that although wildfires are often considered a regional or local risk, smoke impact or smoke can impact PV performance very far away from the actual location of a wildfire. And often we'll see smoke traveling even thousands of miles to impact performance of assets in entirely different geographical regions. It's also important to understand that all of this particulate matter has to settle eventually, which you might have guessed means soiling. Underestimating the amounts of historical particulate matter in the air at a specific location, which can be quantified in SolarAnywhere, can be a major factor in identifying a soiling strategy. And so we also offer two soiling models in SolarAnywhere. We offer the Kimber and the HSU model, which can help understand the potential impacts of soiling per location while taking into account things like cleaning schedules, precipitation, and different asset configuration specs. I'll also mention that the impact of smoke on PV performance is an area of active research amongst our team. And while we don't yet provide data on the explicit impact of smoke on asset performance within SolarAnywhere, like what is shown on the left-hand side of the screen, it's something we're definitely looking into. And we're also considering how smoke might be of impact in the future and better ways to quantify the risk of smoke impact rather than just considering the frequency of historical events. So definitely stay tuned for more information from our team on this topic. And so next, I will turn it over to Laura to do a quick demo of the RatedPower platform.
Okay, thank you, Evan. That was very interesting information, honestly, for me too. Let me share screen. While I do that, hope I can do it properly. Give me a sec. I want to remind everybody, though, that the chat is open. Ask any questions, okay? There's no bad questions, so go ahead and let us know. Okay, I think you should already be seeing RatedPower. Correct me if I'm wrong, Evan. Can you see it? Just, okay, good.
I can see it.
Okay.
Looks good.
Okay, good, good. So this is the software, guys. This is how it looks like. You see, hi, Laura, this is me. Everybody would have their own accounts. It's cloud-based. And this is a project that we have called Ozona US in Texas. We see over here 5 different designs. They look similar, but they might have different characteristics. And this is the beauty of RatedPower, how you can compare and see which one might be more efficient for you. Right now, I have 2 selected that I did just before. And here we can see how even though they're using the same parameters, the same modules, same GCRs, all of that, we're going to see that because they have a different solar resource, they're having different results as a whole. So this is, in the end, essential to properly design your plant. So yeah, this is what I wanted to show you in terms of comparison. I chose PVGIS just because it's the free version that we have at RatedPower, probably one of the most used because it's free. But apart from that, we have other resources. How would we get there? I just opened one of the projects to show you exactly how it looks like. Let me clone this design, which means that I'm going to be editing it. We work on a project that has already been there. And we have here all of the tabs of the design process that an engineer would go through. On the location tab, we already have here this site, but we can start from scratch. Uploading it. We have our Prism database, for example, which includes location, exclusion zones such as this ones. All of that would be taken from Prism in the US, and you would have it directly here. Once you have that, the software will give you automatically topography and meteorological data. Automatically, we have PVGIS, NASA Power, and NASA SSE, but we have API for other resources, SolCast, SolarGIS, and of course, SolarAnywhere over here, which is the one that we have selected. We have also some details over here, minimum temperature, maximum temperature, and some curves that you're going to be able to see over here. Okay, so this is how it looks like. If we were to select a different resource, we would run the design again, and in about seconds, for the purpose of showing it, let me actually do it, select a different resource, and I would run the design, and this would give me, in seconds, new power, okay? It also calculates energy, it also calculates your financials, LCOE, return on investment, MPV, payback period, substation information, and all of the other things that I mentioned at the beginning. What am I doing? I'm going to go back to the design where we had SolarAnywhere selected. And what the software is calculating for you is all of these key information that you're going to need. By the way, I forgot to mention, not only can you use any of these, but you can also upload your own metro resources. And you can do monthly, you can do hourly, or even you can do even sub-hourly if you want, down to 1 minute resolution. As Evan was mentioning before, resolution is key. So you would be able to do this over here. With that, some of the documents that we generate that are going to be key for this would be the energy yield report, of course, also the yield results. And let me actually just go ahead and quickly show you how this looks like. Although I'm thinking now that you're not going to see it. Whew, do I want to change my sharing screen? Am I going to be that daring? Guys, I think I want to share it with you later on because I don't trust myself in showing some other thing. But we would provide for you all of those yield results, the energy yield report. We'll share it later with you guys, and some other resources such as drawings in CAD, single line diagrams, and as much information as you want over here. With that being said, I think that's about it for RatedPower. I'm not going to go and do a full demo, but they're always available if anybody here wants to know more. And I think that's it. I'm going to stop sharing for now, unless somebody asks more about RatedPower. Thank you, Evan. So we're back at our last slide today, which is about question, guys. Okay, I see some of you had questions over here. Let me go ahead and ask the first one. So, what is the level of certainty associated with SolarAnywhere resource data, and can they be used for bankable feasibility studies? Have any third-party evaluation of SolarAnywhere data been done to assure users of data accuracy in comparison with other well-known ones? That's a long one. I think this is for you, Evan. Let me know if you need to reread it.
Yeah, that sounds like for me. So in short, yes, our data is bankable. Our historical data has a global MBE close to 0 in many regions. I think globally it's around 0.7%, and has a measured global certainty at a 95% confidence interval between negative 3.5% and 5%. And so we publish our own validation annually with each new model version release, and we validate against hundreds of MET stations and ground data around the globe and in different climate regions. I think you also asked about third-party evaluation. Fraunhofer has also done a third-party validation of our data in Europe, which similarly proved the accuracy that we see globally within our validation. So yeah, we definitely compare to others in the space.
Okay,
and
well answered.
Actually, real quick, yeah. Laura, I'll also mention we can include a copy of our validation white paper in the follow-up email after this event.
Yeah. Good. We're going to be sharing lots of information, guys.
Yeah.
Okay. Second question is, I think this one is for me actually, and is, do you also accept different resources for topography data? Good question. For now, we do provide automatically Google Earth data, but we allow our clients to also upload their own topography. So it's not that we have APIs such as with you guys, right? But you would be able to upload it directly as a CSV file. Okay, hope that answered it. Otherwise, let me know. Let's go to the third question. Do you see an advantage in performing site adaptation based on a year ground measurement? What is the maximum drop in long-term GHI we can have after site adaptation?
Yeah, great question. I think that's for me. So yeah, there are huge advantages to performing site adaptation or a tuning study where you tune a full set of historical data, so say 25 years in the past, to say a years of ground measured data at that same location. And so this is actually a service that SolarAnywhere offers. I will definitely say it's important to have at least a year's worth of ground data to do this in order to account for that seasonality. But with the year's worth of data, we're usually able to tune the bias of a historical data set to 0 with a 1.2% in uncertainty. And our team has actually published a white paper on this specifically that can be found in our support center website. So I'll also make a note to share that link to our support center page after this meeting in the follow-up email.
Okay, good. Next question. You talked about the wildfire impacts, which was interesting, but how does SolarAnywhere help with other extreme weather events such as hurricanes or hail?
It's a great question. So these are really big topics in addition to wildfire right now. Right now, we only offer wind data, so gust, direction, and speed to account for things that might be picked up like as historical hurricane events. Hail is a tricky one. There are some other third-party data sources that people can acquire hail from, but it's an area that our research is looking into. We don't offer hail data at the moment, though.
Okay, good. What else is here? We have one about albedo data. Do we also provide albedo data? And I think this might be for even you and I, right, Evan? I don't know. You work with albedo data, am I correct?
We do, yeah. So we do offer albedo data, and I think RatedPower intake albedo data, right? Right, Laura?
That's correct, yes. You can, we don't have an API, let's say, for albedo data, but for sure we take that into consideration. You can select your own grounds, modest data, or import it too, so.
Yep.
Definitely. Okay, what else is here? Does resolution have marginal returns? What is the optimal resolution if it is so critical to solar resource assessment?
Yeah, good question. So I think that depends if we're talking about temporal resolution or spatial resolution. Temporal resolution will always provide more accuracy in terms of resource variance. Spatial resolution might have marginal returns, I would say, if you have a very large project footprint and you want the entire area represented in the irradiance model rather than a specific point or portion of the asset. So in this case, we see most customers using 1 kilometer spatial data, as it can typically cover a good portion of the asset, or you can pull it at multiple locations over an asset to truly represent the surface area. I will mention it's possible to interpolate data or upscale imagery of data to produce even higher resolutions, but the accuracy of that resolution might be less if you're creating these synthetic data sets. So it's really important to have native resolution, which is what we offer at 1 kilometer and 500 meter in some locations, because that synthetic resolution might not provide any benefit or have diminishing returns at some point. Another note here, I guess we'll talk about data processing. Right now, we don't see diminishing returns for processing more data at higher resolutions, but theoretically, at some point in the future, you might see that if you're trying to get really minute.
Okay, perfect.
Yeah, thanks.
I feel that, Evan, because I think most of these questions are for you. So take a breath, because this one is again for you. Okay.
Okay.
Here it goes. How are large forest fires affecting soiling and TMY irradiance, lingering smoke?
Yeah, so we talked about this a little bit in the presentation, but smoke can have huge effects on soiling and impact performance of an asset. So the important thing to consider here is that soiling from smoke can occur very far away from an actual fire. It's really dependent on wind direction and wind speed. So say if you're considering a site directly west of a potential fire and you tend to have westerly winds, additional attention to soiling, might need to be considered. But you can use our soiling models or other soiling models to help account for those impacts. You can also compare particulate matter data at different locations over long histories to help predict, the impacts of soiling potentially in the future.
Okay, thank you. I'm going to ask this question. I'm not so sure if it's for me. I'll go ahead and answer what I can. It says, does the software accept ground station data besides the satellite database? I'm guessing this means for RatedPower, in which case right? Or Evan, or does this make more sense for you?
I think that makes sense for RatedPower. I'll mention our satellite data doesn't account for ground data.
It's exactly, that's it. For us, it doesn't really matter, honestly. We have different resources. Some of them are not satellites. You just need to import your own TMY, CSV data, however you want to import it, and it will be taken into account for sure. So, okay, thank you. Lots of questions. I love it. What else do we have here? Now I'm lost on which ones have we answered and which ones we haven't. Is the spatial resolution dimension in area kilometer square or kilometer as mentioned in the presentation?
Yeah, so the spatial resolution would be kilometers squared. Yeah, so it's 1 square kilometer or 10 square kilometers or 500 meters squared that we offer the spatial resolution in.
Okay, perfect. I have another question here about bankability. I like this one. This is for RatedPower. Is your software bankable? Well, bankability is the tough one. What is bankable? It means that banks accept it, right? If you are a user that is trying to get your project bankable, it depends on the bank, honestly. And banks trust results that come from PVSys mostly, right? So because of that, we're trying to change that process. But in the meantime, what we can do is that we can allow our users to have a file, PV Collada file is called, so that you can import into PVSys and replicate their results. We had a third party compare our results in 2D, which those of PVSys, and with the same configuration, they're almost the same. We're talking about 0.4% difference, is very little. So yeah, just that being said, there are different codes, and we have clients that go with both the yields of PVSys plus all of our yields and our other documents. So I don't know, we can say we are bankable, but we are in the process. We do have the report available, so we'll also add that to sharing after this webinar. Okay, this one hasn't been answered. Okay, it has long been studied that the upper atmosphere physics are only a surrogate for what's happening in the atmospheric surface layer. Furthermore, remote sensing products add another layer of abstraction on top of this. Backscatter phase shifts to velocity. I feel like I'm reading Chinese, I'm sorry. But this one's for you, right, Evan? Please describe how you quantify the error between remote sensing products and inside observations. Okay, yeah, that makes sense.
Okay, yes, I got that. So I think this question is asking about the process or techniques we use to compare and measure the accuracy of our satellite model against measurements taken directly at the site. So alluded to this earlier, but we perform a very thorough validation of our historical model with each new data version that's published. And this validation includes many different measurements. It considers global horizontal irradiance and direct normal irradiance, so GHI and DNI. And we follow a very strict QC process of data quality for ground measurement data and pyronometry class and calibration in terms of what we validate against. So again, our model only relies on satellite imagery. It is not tuned based on ground data. We only validate against ground data globally. So yeah, all these details are included in our validation white paper, but that's our process for measuring against ground data.
Okay, perfect. Thank you for that one.
Yep.
Another question here. Do you provide a demo version of the software? We do provide demos. So yeah, just write us. We can show you the software. And furthermore, we do have like a guided tour in a way in which kind of shows you what you can do along the site and navigate through it. So we would love to do a demo for you. Okay. And we run out of questions. Amazing. Those were a lot. Thank you, everybody.
That was great. That was rapid fire.
Yeah, for sure. We have 2 minutes. If anybody wants to ask anything, feel free. Otherwise, I don't see any other coming. We'll be sure to send the recording once again, okay, everybody? Don't worry about that. Hope you liked it. Evan and me, you have there our emails. Please write us if you have any questions later on, or you want a demo, or you want to purchase the SolarAnywhere data, or you want anything, just write us, okay? And having said that, we do lots of webinars from the RatedPower site. Feel free to join our next one, please. Hope this is good information for you guys. And I think we can stop here. Evan, any other thing from your side?
No, thank you all very much. Thank you, Laura, and thank you, RatedPower team.
Thank you, always a pleasure. Have a good day, everybody.